I've got to use this mic. Someone's walked off with the other microphone. All right, so we were talking about floating point arithmetic in the last class. We're going to hopefully finish off that lecture today, maybe in the next class. Before I continue, though, there is I guess it's a fairly well-known document where a lot of this material comes from. So if you search for what every computer scientist should know about floating point what? What's the full title? Floating point arithmetic. There you go. You will come across this document. And so this was written by a computer scientist by the name of David Goldberg. You can see it was published quite a long time ago. So it was in 1991, which actually I guess is a long time ago now. So the IEEE floating point standard has been around quite a long time. I'm pretty sure he's one of the people who helped contribute to the standard. And so if you want another reference for this material, you can always look at this document here. All right, so picking up from where, well, let's go back and review a few things before we continue, just so that we're clear on what's going on in this lecture. Let's do this. Okay, so let me just go back here. Okay, so remember we're talking about floating point math. Now, on your computer, everything's in binary, right? So everything's zeros and ones. So the floating point representation is also zeros and ones. It's awkward to work with zeros and ones. So I'm going to work in base 10. I'm working with a very simplified representation of floating point numbers, and that's just to make giving this lecture a lot easier, right? I don't have to write down 30 digits or something crazy like that. So all of our numbers are going to have an integer part called the significand, right? They always have 3 digits in the significand, and the first digit is not allowed to be 0, right? So there's always 3 digits then. And then we have an exponent here. So there's 1 digit used for the exponent, so a value between 0 and 9. It's also integer. And then we subtract a value from it so that we can get negative integers as well. Right? So all of our numbers will be written as a 3-digit integer times 10 raised to some integer exponent that's between -5 and 4. Okay, so we saw that when you use this representation, a bunch of odd things happen. Well, they're unusual compared to how real numbers work, right? But this is the way they actually work on a computer, right? So the difference between adjacent floating point values. Oh, so first of all, there's only a finite number of floating point values, right? Because we have a finite amount of memory. Point number 2, the difference between adjacent floating point values changes as the magnitude of the number changes, right? So here the difference between these two floating point values, which are as close together as we can make them, right, is 1 times 10 to the -5, right? As soon as the exponent goes up by 1, then the difference between those two, the difference between any two floating point values now changes to be between 1 times 10 to the -4, right? And you can see it all the way at the end here when we have an exponent of 4, right? The difference between two adjacent floating point values is now 10,000, right? So we can't represent the number 1,000,001. The best we can do is write down the number 1,000,000. Okay, and so whenever you change order of magnitudes, that value here, this difference, changes, right? So that digit that's in the last place in all of these examples, that's called an ULP, U-L-P, right? Unit in the last place, right? So the distance between adjacent floating point values depends on the value of the exponent. That distance is called an ULP, right? If you want to know what an ULP is for any floating point value in Java, you can ask the math class using its method called ULP for some value, and it will tell you what an ULP is for that value. Okay, so back here, 1 ULP would be 1 times 10 to the 4. For these two values here, 1 ULP would be 1 times 10 to the 2, right? It would be equivalent to 1 times 10 to the 2, right, or 100. Here, 1 ULP would be equivalent to 1 times 10 to the -4. Okay. So we want to compute errors. So there's something called absolute error. Absolute error is just the difference between the true value. So x hat is always my true value, right? And x is my calculated value or estimated value, right? So the absolute error, you just subtract them and take the absolute value, right? If you use this little formula here and you go back to this table here, right, you can easily show, right, that when I take some real number, and try to make a floating point number out of it, then the error, right, in converting that floating point number to in converting that real number to a floating point number is at most half an ULP, right? So 1/2 an ULP, right? And again, it's pretty easy if you just go back to the table. Whoa, sorry. Right, so let's use a value somewhere in here, right? So if I try to write down the value 10,500, 10,050, I can't get there, right? So I can't write 10,050 because I need a digit in that 4th place, right? So the closest I can get is 10,000 or 10,100, right? So what's the difference between either one of those numbers and 10,050? Well, it's 50, right? 1 ULP has a magnitude of 100, right? So that's equal, so 50 over 100 is 1/2 an ULP, right? So just writing down a floating point number and, just writing down a real number and converting it to floating point almost always introduces some error. All right, so to calculate these errors, so suppose you had 2 values. So suppose you actually knew what your true value was, right? So I know what x hat is. You got your calculated value x. I want to compute the error in ULPs, right? And then the way you do it is you just follow this little algorithm here, right? So you take your true value and you write it down using your floating point representation, right? So I write down the value using 3-digit significand and a 1-digit exponent, right? And then you write your calculated value, right? Also using a 3-digit significand, but this time you have to use the same exponent that you used to write down x hat, right, your true value. Right? So you might not have 3 actual digits here, and you might have decimal places after the digit when you do this, right? Because you need to force the exponent to be the same, because I need that exponent to calculate what an ULP is for that value x hat. Right? And now you just subtract the 2 values and take the absolute value. Right? So let's look at an example. Right? My true value is 1.29. Right? My calculated value is 1.25. What's the error in ULPs? Right? Well, take my 1.29 and write it as a using my floating point representation. Right? So I write it as 129. Right? 3 digits raised to some exponent. Right? So that's raised to 10 to the minus 2. Right? Now I need to write down x. Also using this representation, making sure I keep that exponent the same. Right? So in other words, I need to write down x using an exponent of 10 to the minus 2. Right? So in this example, it turns out to be 125 times 10 to the minus 2. Right? Now just subtract the 2 values, you get 4, right? Times 10 to the minus 2. Right? And ULP in this case is 10 to the minus 2. Right? So in this case, the error is 4 ULPs. Right? So once again, write down your true value in your floating point representation. Write down your actual value using your floating point representation, but make sure the exponent is the same as the true value. Then just subtract the 2 values. Hi, thank you.
I'll just set this up. It's
Super.
just on the wrong frequency.
Okay. Awesome, thanks. All right, so let's look at another example here. Right, now my true value is 12.1. Right, my calculated value is 0.5. Right, so take the 12.1, write it down in your floating point representation. So it's 121, right, times 10 to the minus 1. Right, now write down the 0.5, also using the exponent 10 to the minus 1. Right, so that's just 5 times 10 to the minus 1. Right, subtract, you get 116. Right, for the value 12.1, 1 ULP is 10 to the minus 1. So that's 116 ULPs. Right. Okay, now sometimes your true value is a real number as opposed to a floating point value, right? So maybe you want to calculate how close can I compute pi, right? So pi is 3.14 and then some infinite number of digits, right? If you want to calculate the error in ULPs, you just write down pi, or in this case, this number here, right? Using your floating point representation, and you keep all the digits that you have. So even though our floating point representation only has 3 digits, for the true value, you can keep as many digits that you can keep all the digits that you have. Right? So write down x hat in its floating point representation. So that's 592 point something, right? Times 10 to the 2, right? Write down your second number, making sure you have that exponent, right? Making sure you use the same exponent as x hat. So that's 589, right? Just subtract. right? And you get 3.875603 ULPs, right? So the trick is always write down the calculated value so that it has the same exponent as your as the true value. Okay, so relative error is just the absolute error divided by the true value. Okay, so when you compute relative error, you don't use ULPs, right? You just use regular old math, right? So you use real values for this. I'm not going to go through any examples because we're not really going to look at relative error in this course, right? But if you ever see the term relative error, that's what they're talking about. All right, now, what happens when you subtract or add two floating point values? Right, so you know that we only have a finite number of digits, right? So when you add or subtract two values, it's not unusual if you an extra digit or two. Oh, it's working still. Okay, yep, it's working again. All right, so if two floating point operands have the same exponent, right, so we got the same exponent, when you write it down in its floating point format, right, then addition or subtraction is performed simply by adding or subtracting the significands. Right? In other words, you just add or subtract the integer parts. Right? So 12.1 and 63.8, so just write them down in your floating point format. Right? What's 12.1 in our format? Well, it's 121 times 10 to the minus 1. Right? What's 63.8? Well, it's 638 times 10 to the minus 1.
I will be back.
All right.
Receiver's bad.
Okay, thanks. Right. Go ahead and do the sum. Right, so the sum 759 times 10 to the minus 1, right? And we can actually write down the sum in this case. So we can actually represent our sum in our floating point format, right? We've got 3 digits here, that's nice, right? I've got an integer exponent here, that's nice. I can actually write that down, right? So in this example, we can actually represent the sum using our floating point format, right? Another example is here, right? I have 81,500 and 13,600, right? Just write them down in their floating point representation. In this case, the exponents are the same, so I can just add the significand, right? And I get 951 times 10 to the 2. So again, we can write down that sum using our floating point format, right? Now, the problem happens, what are we going to do if we compute a sum or difference where there's an extra digit becomes involved? Right? So if the result produces an extra digit, then you write the result using the extra digit and round to remove the digit. Right? So remember, we can only have 3 digits in the significand. Right? If we end up with a result that requires 4, right, you write down the result using the extra digit and then round to remove that digit. Right? So here's 82.1 and 63.8. So just write them down in their floating point formats, right? In our floating point representation. Now when I take their sum, right, the significand has 4 digits, right? But our representation doesn't have 4 digits, it's only got 3. Right? So I have to do 2 things here, right? I need to write 1459 times 10 to the minus 1 using only 3 digits in the significand. Right? So in other words, I need to make that 145 145.9, right? And to do that, I'm going to multiply that exponent by, well, I'm going to multiply the 10 to the minus 1 by 10, right? And so that changes that exponent to 10 to the 0, right? And now I've got 145.9 times 10 to the 0, so now I round so that I only have 3 digits, right? So when I have 145.9, you round that to 146, and away you go. Right? Notice now that your sum has an error in it. Right? That sum there is not the actual sum. Right? The actual sum is, what is it, 145.9. Right? The best I can do in our format, though, is 146. Right? So the process of adding 2 numbers can introduce error in the result. Right? Subtracting 2 values will do the same thing. Right? If you take a number and subtract a negative value, you can introduce an extra digit in the result. Okay, here's another example, 81,500 and 93,600, right? Scribble down our 2 numbers, right, so that their exponents are the same, compute the sum, right? I have 4 digits, so what am I going to do? I'm going to increase the exponent by 1, so that goes to 10 to the 3, right? That's the same thing as multiplying by 10, right? So I divide this by 10 and get 175.1, right? Round the result to 175, right? And again, notice that the sum has some error in it, right? It's no longer 175,100, right? The closest I can represent in our format is 175,000. Right. All right, now what happens if your operands have different exponents? Right? Then so what you do is you take the operand with the smaller exponent and you scale it so that the exponents are equal. Right? So here I've got 4 million something and 12.1. Right? So you start with the larger value. Right? So I write down the larger value, that's 432 times 10 to the 4. Right? Now I take the smaller value and write it down using the same exponent as the larger value. Right? And so when I do that, I end up with 0 point, a bunch of zeros, 121 times 10 to the 4. Right? And so now you just compute the sum. Right? You know that we can't keep more than 3 digits in the result, so you so the 3 digits here, in this case, get discarded. Right? And so you end up with the final result of 432 times 10 to the 4. So notice what's happened here. So there's a couple of things that's happened here. Right? So first of all, I need a total of 8 digits to actually compute the result. But I've only got 3 in my floating point format. Right? And so right away, you've got a problem. Right? Notice the other weird thing that's happened here. Positive value plus a positive value, right? So x plus y, right? Where y is not 0, right? But the final result is equal to x, right? So it's possible when you're working in floating point values, right, that x plus y equals x is true when y is not 0. Right, which is weird, but that's the way it works in floating point arithmetic, right? So floating point arithmetic is only an approximation of what happens with real values, right? One of the approximations is that you end up with weirdness like this, right? If y is much smaller than x, then it's not unusual for the case to be when you compute the sum that you end up with that you just end up with x in the result, as the result. Sorry. Okay, now, notice that just to compute this result, if I wanted to compute this result, I have to use 8 digits to compute the result, right? Because the 2 operands, their magnitudes are very different, right? Now, the problem is on your actual computer, especially back when computers were first invented, you didn't have those extra digits, right? So using extra digits is not always feasible in computer hardware, right? So it's definitely back when computers were first invented, you didn't have extra digits, right? If you had, say, 8 bits in your floating point number, you had 8 bits in your floating point number. That was it, right? On modern computers, you do have some extra bits. So I think Intel uses 80 bits to compute results, even though floating point numbers have 64 bits, right? So you actually have 14 extra bits, which is a lot. Turns out to be quite a lot. Right? So on modern CPUs, you do have this extra hardware, right? On older hardware, you definitely don't have that extra hardware. Right? Okay, so we have to decide, well, what are we going to do, right, if we don't have these extra digits, right? So if I don't have these extra digits, right, then what we have to do is you just discard all of those digits to the right of the decimal point. Right? So when I compute 4,320,000 plus 12.1, right? You write down your 2 numbers, writing the smaller number so that it has the same exponent as the larger value, and then discard all of the digits that you don't have. Right? And so here you end up with 432 times 10 to the 4. Right? That's the same result as the previous slide. Okay, now if you don't use an extra digit in your floating point representation, right, then when you add and subtract values, you can end up with very large errors. Right, so here's an example, 10.5 minus 9.98. Right, now that looks like an easy value to calculate. Right, you can definitely all do it. Most of you can probably do it in your head. Right, what happens when you try to do this using our format, where you discard any extra digits that you don't have? Right, so I'm going to discard everything to the right of the decimal point. right? So my algorithm says, right, 10.5 is a larger value. So write it down in our floating point format, right? So we get 105 times 10 to the minus 1. Right? Now write down the second number so that it's using the same exponent as the previous. Right? Okay, so 9.98 is 99.8 times 10 to the minus 1. Right? Discard the 8 because I don't have a digit to represent that 8. Compute the result. Right? So now I get 600 times 10 to the minus 3. Right? So that's x minus y is 600 times 10 to the minus 3. Right? Now, what's the true result? Right? So if you actually do this, if you actually work it out, it's actually 0.052, right? Or 520 times 10 to the minus 3, right? So what is that error in ULPS, right? So that's the true value, 520 times 10 to the minus 3. My calculated value is 600 times 10 to the minus 3. Exponents are the same, so I just subtract and I get 80. Right? That's 80 ULPS of error, which is enormous. Because the standard, right, the IEEE standard says that when you add or subtract two values, I think when you multiply or divide as well, right, the standard says that your answer must be within 1/2 an ULP of the true answer. Right? So you must be within 1/2 an ULP, but we're 80 ULPs away, so we're 160 times too big in terms of our error, right, which is terrible. Notice that the absolute value of the error is relatively small, right? It's 80 times 10 to the minus 3. But when you compare that value to the true value, right, you realize that, oh, that error is actually large relative to the true value. Right? Okay, so let's suppose that we actually can afford to use some extra digits. Right? So when we compute our results, let's suppose I can add 1 extra digit, right? Or 2 extra digits, or 3 extra digits, right? Or so on and so on and so forth, right? So every time you add an extra digit so that you can compute a floating point result more accurately, right? We call those digits guard digits, right? So let's introduce 1 guard digit, right? So in other words, I'm allowed to calculate things using 4 digits, and then I'm going to round the result back to 3 digits, right? So I get to use 4 digits now. So 10.5 is 105.0 times 10 to the minus 1. Right? 9.98 is 99.8 times 10 to the minus 1. Right? Now calculate the result using that extra 4th digit. Right? So now I get 5.2 times 10 to the minus 1. Right? Now can I write 5.2 times 10 to the minus 1 exactly in our representation? The answer is yes. Right? Because there's only 2 digits in that number. Right? And the exponent isn't so small that I can't write down the result. Right? Yeah. Right? So 5.2 times 10 to the minus 1 is equivalent to 520 times 10 to the minus 3, which I can represent in our floating point format. Right? And so notice what's happened here. You're now able to calculate the correct result, right, just by introducing 1 extra digit in this example. Right? So introduce 1 extra digit, we can actually calculate the correct result. So it turns out if you just use 1 guard digit, that's not sufficient to ensure 1/2 ULP error. Right? So for example, here's 110 minus 8.59. Right? So the true answer is 101.41 or something like that. Right? So just apply the algorithm. Right? I get 1 guard digit, so 110 is just 110.0 times 10 to the 0. Right? What's 8.59 using 10 to the 0 as the exponent? Right? Well, it's 8.5. Right? I only get 1 guard digit, so I lose the 9. Right? So I lose the 9. And so now you calculate the result, and you get 101.5 times 10 to the 0. Right? I've got 4 digits in the answer. Round to get 3 digits. Right? That gets me to 102. Right? Times 10 to the 0. The true value is 101.41, and that's almost 0.6 of an ULP. Right? So that's a little bit larger than what the IEEE standard says that I'm allowed to have. Right? And so it turns out if you're working in base 10 you need at least 2 guard digits to ensure 1/2 ULP error. All right. Any questions so far? This is all very mechanical. You just have to remember to apply the steps in the right way, right? So if you memorize that little, if you just memorize that little slide back here, where to go? Sorry. Right. So when you, where the heck is it? Sorry. Okay, so if you just memorize these slides starting here at addition subtraction, right, you can always calculate the correct result. Right? It's all very mechanical, so you just have to remember the steps that are involved. Okay, something funny happens when you have two floating point values that are almost the same, and then you subtract them. So subtracting two similar floating point values results in something called cancellation or loss of significance. Okay, so I've got two 10-digit floating point values, right? So I actually have I actually am able to have 10 digits in this example. All right? So I've got two values, they're very close. In fact, they only differ by 1, and the difference is in that last digit there. Right? Sorry, the difference is in the last 2 digits here. Did I write this down right? I think I might have written this. No, okay, I think we're good. Right? So 10 digits, they're very close together. The two numbers are very close together. If I subtract them, right? So in this example here, you end up with 1 times 10 to the 0, right? And then to convert that to a floating point into a 10-digit floating point value, right? I have to make sure the first digit's not 0, so that's 1, and a bunch of zeros times 10 to the minus 9, right? Now, notice that answer, there's only one significant digit in that answer, right? There's one number that's not 0, everything else is zeros, right? So the difference has one significant digit, even though x and y both have 10 significant digits, right? I guess you can argue x only has 9, but anyway, it's fine, right? Okay, so this phenomenon is called cancellation, right? Why is it called cancellation, right? Because I've got 10 digits here, 10 digits here, 10 significant digits here, compute the answer, and then all of the digits in front become insignificant, right? So you now have an answer that only has one significant digit, right? So we say that the leftmost digits, or the high order digits, or the most significant digits of the operands cancel one another out, leaving only the rightmost digits, right? So what does this mean, right? So when you look at these two numbers, right? So if I look at the digits in the front of this number, right, those contribute more to the magnitude of that number than that digit does, right? This digit over here only contributes like 1 through 9, right? 1 through 9 parts in 10 digits, right? Whereas if I change this digit, right, that changes the magnitude of the number a lot, right? So the numbers at the leftmost, the digits at the leftmost side of the number, right, those matter more to the overall value than the numbers on the right. If I subtract two approximately equal numbers, all of the leftmost digits go away, right? They all become 0. Right? Now, if the two operands contain no error, then there's no problem. Right? So if my two values really are those two numbers there, and you subtract them, well, then the answer really is 1 times 10 to the 0. Right? So that's fine. The problem is what happens when those two numbers are not exactly those values. Right? So if the two operands contain no error, then we call this benign cancellation, meaning there's actually not a mistake and there's no actual significance to this. Right? If your two values that you're working with contain some error, then it's possible to end up with what's called catastrophic cancellation. Right? So when one or both of your operands contain error, when you subtract the two values, you can end up with an answer that's very, very far off from the correct answer. Right? Now, you might say, well, when do I ever have error in my operands? The answer is you always have error in your operands, right? So I take a real number and try to write it in floating point. Almost always you can't write down the number exactly, so there's some error. If you take two floating point numbers and do some calculation with it, there's probably some error introduced. Right? So whenever your operands are computing using floating point arithmetic, right, there's a possibility that this catastrophic cancellation might occur. Right, so this is an example using the quadratic formula. Right, so inside the quadratic formula, you have to compute this quantity b squared minus 4ac and then take its square root. Right, what happens if b squared is almost equal to 4ac? Right, so for example, right, when b is 3.34, a is 1.22, and c is 2.28, right? Just do the math, right? So crunch through the results, and you end up with the true value. So this is calculating the true value. This is not calculating the result using floating point arithmetic, right? So the true value is 292 times 10 to the minus 4, right? So that's what you should actually get, right? But what happens when you use our floating point representation, right? So what's b squared? Right? So 3.34 squared. Are these numbers right? B3. Yes. Okay. So when you compute b squared, right? 3.34 times 3.34, right? If you remember your algorithm for multiplying real numbers using by hand, you'll realize that you could end up with 6 digits, and you do in this case. Right? So you end up with 111.556 times 10 to the minus 1, right? 11 and a bit, right? What's wrong? Our floating point format can't hold those 3 extra digits, right? So when I compute b squared, I end up with 112 times 10 to the minus 1, right? So instead of ending up with 11.1556, I end up with 11.2, right? And that's if I round. So what happens when you compute 4ac, right? So if you calculate 4ac using the values on the previous slide, you get 111.264, right? Again, 6 digits in the answer, but I can only hold 3 of them. So now I get 111 times 10 to the minus 1, right? So that's b squared, that's 4ac. So now I subtract the 2 results, right? Well, they have the same exponent. One's 112, one's 111, so the answer is 1 times 10 to the minus 1, right? Or 100 times 10 to the minus 3, right? So that's my answer when I compute the result using the limitations of my floating point format, right? 100 times 10 to the minus 3. What's the correct answer? It's 292 times 10 to the minus 4, right? None of those digits, right, are correct, right? Not a 1. The exponent's not correct either. Right? That exponent is minus 3, this is minus 4. Right? What's the error between the two? Right? So if you calculate the error in ULPs, it's 708 ULPs, which is enormous. Right? This is interesting. So the 2 intermediate values, right, are calculated to within, are they correctly calculated? Yes, they're correctly calculated to within 1/2 an ULP. Right? B squared and 4ac, those are correctly calculated to within 1/2 an ULP, which is what the standard says has to happen. Right? The difference is correctly computed to within 1/2 an ULP. Right? But when you compare it to the true answer, right, you now have an error of over 700 ULPs, right? Which is very large relative to the correct answer. Right? So this phenomenon happens, and there's nothing in general that you can do to avoid it. So when you're working with, when you're computing values that are very small, and they're small because you took 2 values and subtracted them, right, you have to be always suspicious of that answer, right? There's a good chance that that answer is badly off. Now, every once in a while, you can play some tricks and avoid. So you can take whatever thing you're computing, right? You've got some formula that you're computing. You can rearrange that formula or transform it so that that cancellation doesn't happen, right? This doesn't happen very often, so it only happens in very specific instances. So you've got some mathematical expression, right? And then you realize, oh, parts of this expression are equal to something else, right? I can substitute those something else and avoid the subtraction that happens, right? If you go through the floating point error notebook, you'll have, I think, 2 or 3 examples where you can apply some mathematical transformation and avoid the catastrophic cancellation. Right? Okay. So that's catastrophic cancellation. Now, what happens if you don't have, you're not subtracting things, but you're just adding things together or multiplying or something else, right? Now, it turns out one of the things we do a lot of these days is we add lots and lots of values together, right? So, for example, if you need to compute an average or the standard deviation or some sort of statistic with a large number of values, right, you typically end up computing large sums. Now, what's the problem with that? So the problem is whenever I compute one of the many sums that I have to compute, right, that intermediate sum has potentially 1/2 an Alpen error in it, right? Now I add it to something else, right, and that's another 1/2 an Alpen error, possibly. And then I add it to something else, and that's another 1/2 an Alp, right? And so it's possible that you can accumulate error if you're doing a long sequence of mathematical operations, right? Such as computing a sum so that I can compute an average, right? So here's a little example. So here I'm going to sum 1,001 floating point values, right? So not a lot, actually. There's only 1,000 values. That's, I mean, for things that people compute today, that's like nothing, right? Like it's not uncommon to work with billions of values these days. So here I've got just 1,001 values. I'm going to use float in this example to make the error more obvious, right? I'm going to put in 0.1 1,001 times, right? So if I take 0.1 and I add, if I take 1,001 0.1, oh wait, and then I'm going to insert the value 1 million at the front, right? So I've got 1 million, and then I've got 1,000 0.1s. And then I'm going to compute the result, right? So I've got 1,000 0.1s, so that's 100 when I add them together, right? If I add that to 1 million, I should get 1,100,000, right? If you actually run this code in Eclipse, right, or in a Jupyter Notebook, the value that gets printed out is 1,125,000, right? So I can't even sum 1,000 values without introducing I guess 25 units of error in this case, right? And that should surprise you, right, in this case, right? But it really does happen. All you have to do is run this code, and that will in fact be the result, right? Okay, so what's the problem here, right? So if you think about what I've done here, right? So I stuck 1 million at the front of my array, right? Right, so I've got 1 million here. And then I've got a bunch of 0.1s, right? So 0.1, 0.1, 0.1, and so on and so on and so on, right? So why does this sum end up having so much error, right? So I got 1 million and 0.1. So when I add those together, right, the magnitude of these two numbers is very different, right? Based on everything else in this lecture, you know that that sum is probably going to contain some error, right? In other words, a lot of that 0.1 is not going to make it into the sum, right? Because that number is so much smaller than this one, right? And then I've got a number that's roughly 1 million plus another small number, right? And then I've got a number that's approximately 1 million plus another small number, and so on and so on and so on, right? And so that's the reason this ends up with so much error. You can fix it in this case, right? All you do is you stick the million at the end of the array, right? And put all of the 0.1s, all the smaller values at the front of the array, right? So when I move that million to the end, right? So if I move that to the end over here, and then compute the sum, well, I sum two values whose magnitudes are the same, right? So there's no error, or very little error, right? And now I've got a number that's 0.2, or roughly 0.2, and add that to 0.1, right? So again, relatively little error when I sum these two together, right? And so on and so on and so on, right? And so when you sum it with 1 million at the very end, in this case, you actually can produce the correct result of 1,100,000, right? Even though all of the intermediate sums do have some error in them. Okay, so if you Google this problem online, right? So you say, I've got a bunch of numbers, I need to sum them together, and I have to avoid error as much as I can, right? And then what you'll often encounter is you'll see people say, oh, well, you should just sort your array or list, right? Sort them from smallest to largest, right? So that is often recommended as a method of reducing rounding error when summing many values, right? Usually, often it works. It doesn't always work, right? And there's also other reasons why you might not want to rearrange or sort the elements of your array or list, right? So number one, you might not be allowed to sort your array or list, right? Because someone's given you an array or list and they don't want it sorted, right? They've given you this array or list for a reason, right? So in other words, the order of the elements is significant, right? So you can make a copy of the array or list and then sort the copy, right? But now you've paid twice the amount of memory to solve the problem, right? Furthermore, sorting that list or array is in big O n log n, right? Which you should know from your previous course, right? If you sum n values, that should only take big O n operations, right? So now you've increased the complexity of your problem, right? So you increased the computational complexity, you've increased the memory complexity of your problem, right? It turns out there's an algorithm called Kahan's algorithm that can, with some clever math, actually sum the values in an array, ensuring, while also reducing the error that you encounter, and it doesn't have to sort. Right, that's also in the floating point notebook, floating point errors notebook, if you're interested about reading that. I think the most recent, so people actually study this problem. There's a very recent paper where someone's come up with a way, without using Kahan's algorithm, to do the sum and still minimize the error. I don't remember the name of the paper, but it's fairly recent. Right? So there are people who still study these sorts of problems. All right, what time do we have here? Okay, so I think that's plenty for today. Assignment 2 will come out hopefully tonight, but I think it may come out tomorrow. So the second assignment will come out. You'll have 2 weeks to do it, so it'll be due 2 weeks Monday. Anybody has anybody finished assignment 1? Anybody have any yes? Anybody have any problems? Okay, so if you have problems, you can still fire me an email before, I guess, 8 o'clock tonight. And I'll get around to looking at it.